We're ready to recommence. Thanks to the miracle of Skype, we have Doug Millar, K6KEY, on the line. He's going to be talking. I'm going to be turning the slides for him. We talk about microwave power sensor limitations. Doug started out as KN6JEY in 1957. He's been mainly interested in VHF and up, has rigs at all bands from 1.2 gigs through 122 gigs, active on EME on 144, 432, 1296, and is preparing a 10 gig EME station. In the 80s, he became interested in metrology and has worked as a consultant in RF power measurement. He was the ARRL technical advisor in measurement and calibration and wrote chapter 26 in the handbook from 94 through 2014. He also does a bit of CWDXing. So I'm going to hopefully have Doug's audio come through the system, and we will go into presentation mode.
Okay. Hello, test. Oh, okay. Hello, everybody. This is my first time to be on this end of Skype, and I'm hoping very much that it works. I wish I could be with you. A big shout out to Mike, KL6M, if he's there. Hi, Mike. And John, I cannot see my slides. Okay, there we go. All right, well, we'll start the presentation. The first picture is one of my favorite watt meters for just general use, and bang for the buck. It probably is the best deal you can get. And that's what the talk's going to be about. Next. Next. Okay, all right, so we're going to talk about sensor uncertainties, and we're going to talk about test equipment and measurement methods, and some of the equipment that I use and other people use for testing sensors and power meters. Next. So as John said, I have a lot of interest and experience in power measurement, but I'm not an engineer. Everything I've learned mainly sort of as a technician. I got a Boonton generator that I'll show you later, and that pushed me into asking the question of how we know the 1 milliwatt on the front of our watt meters is really 1 milliwatt, or how much of a milliwatt that really is. And in my lab work, I ended up really only resolving 4 digits accurately, and it turns out that that might be good enough, and we'll certainly find out as we go along here. Next. Here's a history sort of power meter sensors. A bolometer or a thermistor. I don't know if any of you have 1/100th amp glass fuses and wonder what in the world they're good for. They go into a power sensor for about 1 to 10 milliwatts, and they were used in the early days for power sensors. And really what it is as the fuse was exposed to RF energy, it would change resistance, and that was interpreted directly as the amount of power being dissipated in it. And the thermistors have been used, let's see, the 478 sensor, the one that goes to the 432 meter, those are thermistors, and they're directly traceable NIST, and one of the only ones that does, and we'll say more about that later. A thermocouple is pretty much what it sounds like. On a little tiny substrate, you put a load, a resistor, and on it or next to it, you put a thermistor. And as the resistor gets warm, it changes the voltage that's generated by the thermocouple or thermistor. And that's more indirect than the first system, but that's pretty much universally used in power sensors. And then the third one is a thermopile. Again, what it sounds like is, I think PRD has been the most prolific thermopile generator. And that's a series of thermistors put together, so you yield a higher voltage with change in temperature, and that's actually used in calorimetric measurements. The third one is a diode sensor, and really that's just a diode rectification. Anritsu has a current sensor out that's got a wide range of sensitivity, and they have 4 or 5 diodes that they switch in to get into the linear area of the diode curve. It's very elaborate, it seems to work pretty well, but it's also very expensive. And I think you'd have to add a fourth one. And the trouble with this talk is that as I went along, the goalposts kept moving. New things came out. Every time I looked on the internet about calorimeters, there was something new on. So I kind of rang the gate down on about 2015 and said, okay, that's as much as I'm going to talk about. But you can imagine what a direct sampling A to D converter and FPGA would do to power sensing. And I think Analog Devices has something that does that, and they're pretty good. Anyway, next slide. Okay, the traceability tools are interesting, and most of my information is centered on Bunten and Hewlett-Packard, and I'm sure these names are familiar to you. At one point, Bunten was using an NIST microcalorimeter for DC substitution, and I'll show you a picture of that. The Wandel and Golterman EPM1, a trombone or mechanical attenuator, and a Bunten 2520 for their accuracy. At HP, oddly enough, they measured the 478 sensors that came off the assembly line, and they would find one or two every once in a while that had a ridiculously low SWR, and they would label those H75s. There's two different suffixes, but the 75 is a metrology grade 478 that's traceable, and all it is a lower VISWAR sensor. If you find one, keep it close to you and don't let it go for less than $1,000. They're highly desirable among metrologists. Okay, next slide. Okay, here's a microcalorimeter, and there are a number of them on the internet, and the resource page I have at the end of the talk references a couple of them. But basically, they take a single substrate that's a load, and they put two thermocouples on it. One is for temperature compensation, and the other is for the actual measurement. And they put it in a bell jar, and they temperature stabilize it, and then they measure everything: current temperature and humidity, the loss of the RF cable, the loss of the DC lines, and they just keep knocking down the uncertainties until they're pretty sure they've got things as accurately as they can do. Now, if you've been running a GPS frequency source in your shack, you're regularly dealing with 11 digits of accuracy. If you have a nice DC voltmeter, you've got 5.5 or 6.5 digits of accuracy. If we can get 0.5% at RF, you're almost to the gold standard. That's almost as good as you can do. So these guys are fighting pretty high numbers from our point of view, and you'll see why as we move along. And the calibration is done at 30 to 50 megahertz because SWR is less of a factor at 30 to 50 megahertz. The calibration of attenuators is, at least according to PRD, pretty much the same at DC as it is at 30 to 50 megahertz. And line loss is lower, and so your uncertainty list gets much smaller if you keep the frequency lower. And of course, as you know, that when you plug in an HP power head, there's a frequency versus calibration table that says how to compensate for the differences at higher frequencies, some of the differences at higher frequencies. Okay, next slide. Here's a Wandel and Golderman EPM1. All it does is measure 1 milliwatt, and there are very few of them. The ones I've seen don't have the power head. I found a power head that was as is, where is. If you, again, are really lucky and find one of these critters for cheap, get it, but only with a power head. It's an odd instrument and very specialized and sort of interesting, but in my book, that's about all it is. Okay, the next one. Okay, here's a Bunten 2520. It's ostensibly very simple. The Type N connector puts out the power from 10 milliwatts down to minus 70 dBm at 30 megahertz. And it has a set of attenuators. What they spent their money on was a set of attenuators in there that are used to get the one-tenth of a dB steps down to minus 70. And then in the EEPROM, they store the calibration variables for each one of the attenuators. And you end up with a very, very accurate output at 1 milliwatt, and also very, very accurate output at the lower values. Now I'm going to add something into the talk I didn't have on the slides because it made sense. One way to get the same thing is to use a fairly well-known 1 milliwatt output from, say, a 436 or 435, any one of those meters that puts out 1 milliwatt, and then get a 10 dB and a 20 dB attenuator and read what the output is at minus 10 and minus 20 dB at 30 megahertz. And I want to mention one attenuator, and that's this little SMA guy. It's so good that there's no calibration curve on it. It's a 8493C, 8493 Charlie. What they do is they take a sapphire substrate and they vapor deposit tantalum nitride on it, and they keep the accuracy to 1/100 of a dB, and it's flat on its rated frequency range of 26 gigahertz, but it also is nearly flat up to 32 gigahertz. So if you're dealing at 30 megahertz, this thing is really, really flat and very accurate. Sometimes you can find these cheaply. Generally, they're not burned up, and any value would work as long as you use that as a standard. So that's what I wanted to throw in on the side. I have two of the Boonton 2520s. One is for sale, in case anybody's interested. Next slide. Okay, the output of the 2520 is from 0.7 to 1.2%, which is 0.05 dB. It's based on some really nice standards at Boonton, and you can see the milliwatt difference. If you are within that range, you're within 1.2%. Okay, next slide. Here's the 478. This is not, I don't think it's an H75. The metrology grade ones look just like the other ones, except they say H75 on them. Okay, next. There we go. This is an interesting story because when they came out with new sensors, guys said, well, why don't you just make a better 432? That way it'll be traceable. Well, HP finally did. This is an elaborate power meter. It has a 6.5-digit digital voltmeter inside that measures directly from the sensor to get better accuracy in the measurement. Now, the HP 64-1C app note talks about using a DC voltmeter external from your power meter to improve the accuracy, and you can take a look at that. But this one does it internally, and whatever you can do in a meter to make your readings more accurate, these guys have done it. It's a real tour de force, and in tribute to the old days, it's an N4032A, but not in tribute to the old days. Look at the price, $8,800. So it's there, but that's pretty steep. Maybe in another 20 years, our grandkids can buy one of these for $40 surplus. Okay, next slide. Okay, here's a sleeper. This is am I right, a trombone attenuator? It's a mechanical attenuator made by Eaton or AIL that's principally good at 100 megahertz and below, but it reads out in 1/100 of a dB steps, and it's accurate because the dB attenuation is based on the mechanical linkage and gearing that's used to separate the trombone. So these are really profoundly accurate attenuators for power measurements at lower frequencies. I got this one for $10, and I don't use it every day, but it does the trick. I think the stacking two attenuators and getting 0, 10, and 20 and 30 dB with a good set of attenuators, SMA or end connectors, is probably the easiest thing to do. But this is certainly the most accurate and gives you the best results. Okay, next. Okay, so for my lab, so you know what I'm up against in telling you what I've discovered. These are the sources I have. Use a 34401 voltmeters calibrated Valhalla 2700 DC generator transfer standard, a PRD 685, and I'll bet, John, let's see, does anybody else have a PRD 685 calorimetric thermopile? See if anybody raises their hand. Okay, these are pretty scarce critters, but they were popular in the 60s and then went away. Power meter I use is an 8482. It's calibrated, and the power source is, of course, the 2520. Okay, next slide. Here we are, the PRD 670 thermopile. And it's exactly what it looks like. There's an end connector, you put the power in up to 100 milliwatts. There's a temperature compensating thermopile and DC leads that come out the back. So you put in 2.236 volts, 1 milliwatt at 50 ohms, DC into the input, the RF input, and the output is 0.1160 volts. So if you put 1 milliwatt at 30 megahertz in, you should see 0.1160 volts output. You could probably get more resolution, but unfortunately, everything disappears into the noise after the 0.1160 volts. There's not a, I don't get a stable enough reading to make it worth it. Some digital averaging or something might give me one more digit. But this is basically a calorimeter where heat is used as a transfer medium between RF and DC or DC and DC. Calorimeters are used widely. 434 Hewlett-Packard was an old favorite of mine. Bird uses calorimetry extensively. They have a number of calorimeters, and they all use water as a transfer medium. This just has the thermocouples attached to the loads. So that's my AC/DC, DC/DC transfer standard. Okay, next slide. So what are we up against? The lab uncertainties for RF power measurement are about 0.7%. If you really strain it, you can get down to 0.5%. The practical sources of uncertainty can push us above 10%. So what's the list of uncertainties that adds up to for our measurements? And you can play the next slide. Okay, this is a list of uncertainties from the Anritsu 2400 series power meter instruction book. And if you look down the list, there's some that are not really big. The instrumentation accuracy is 0.5%. That's not too bad. You could probably improve that, but you're running up against right-away sensor linearity, 1.8%. And linearity is not specified by any of the manufacturers of the power sensors. They'll tell you the correction factor, but they won't tell you the linearity. And at almost 2%, that really compromises a really accurate meter reading. Now, you can lessen that by actually measuring it, taking an accurate attenuator and seeing how well your power sensor does as you move down in sensitivity, or down in power level. I found that all the sensors I have, all the HP sensors I have, are different. They're somewhat within spec, but if you hit them with too much power, at minus 20 dBm, it'll push the curve out. So that surprised me. Noise average, 0 set. Those are quite small, but mismatch uncertainty, almost 4%. That's the bugaboo. And it's not just mismatch uncertainty of the load, like if you're measuring a dummy load, for instance, or a power meter that's 49.7 ohms. That's only half the problem. The other half is what you're measuring it with. Both sides need to be measured in order to get a true picture of what the mismatch uncertainty is, and you cannot assume a thing. Reference power uncertainty is 1.2%. I think that's a little high. But you can read down there, and that adds up to quite a bit of inaccuracy. So play the next slide. Here's uncertainties from several of the HP heads. And you can see that below the measurement range, if they specify minus 30 dBm, the accuracy skyrockets. It doesn't just drift off to be a few percent per dB. If it says minus 30 dBm, that's the end of the story. And there are different characteristics, 8481s and the EEPROM sensor. But it's nice to see that visualized so you get an idea of what you're up against on both ends of power range. Okay, next slide. Below 1.1 to 1 adds no more than 5% error to the reading. That's 20 dB return loss. At 1.2 to 1, 9 dB return loss, the inaccuracy goes to 1.5%. So to have to lower your mismatch uncertainty, you need to keep your return loss down, I would say 15 to 20 dB or more. So get your vector network analyzer and measure both ends of it and see what your VisWAR is. Yeah. Sorry, you're right. Uh, it's 2 to 1. Sorry, I printed that wrong. Well, show the next slide. This is a graph of the bottom axis is error from 1 to 4%. The top one is the SWR uncertainty of the, I can't read it. Generator, yeah. Thank you. And the slanted lines are the VisWAR of the calorimeter. And you can see that keeping the SWR low makes a huge difference. If you don't know, or if it's high, then it just takes off to the right. 2 to 1 would, on either side, would almost negate your power measurement accuracy. Okay, go ahead and switch a slide. Okay, I thought this was interesting. This is sensor SWR versus frequency. I'll let you look at that a little bit. It's the 478 is really nice between 100 megahertz and 1 gigahertz. After that, it goes to 1.3 and 1.4%. The 8481 actually has quite a flat SWR, but only up to 4 gigahertz. This is out of the HP book. Oh, and a note somewhere I read in the material that the input coupling capacitor affects the low frequency response, and those of HP sensors that are so good, they change the input capacitor on it to emphasize the low frequency. That way they get better VisWAR. Okay, change the slide. And I thought this was interesting. This is an HP 18 gigahertz sensor, and the SWR goes to 1.5 up to 33 gigahertz. That's not too bad. And the cal factor doesn't go bananas. Now, I know taking an N connector and running it up to 33 gigahertz is asking for trouble, but you might be able to get away with 24 gigahertz and have some kind of accuracy without, I'm not sure what modes you'd set up, but that's the sensor rating, and gives you some hope at 24 gigahertz rather than buying an extremely expensive 24 gigahertz sensor. The 18 gigahertz waveguide sensor works nicely at 24 gigahertz also. Okay, change the slide. Okay, so here's a list of uncertainties. 0.5% for the meter is fixed. 4.5% for temperature. I think you can get that down to 1%. Sensor linearity is 1.8%. I would measure that to make sure what the actual uncertainty was. Mismatch loss, I think you can get to 1 or 2%. And the meter calibrator is more likely 0.7%. All the companies that design those do the same basic thing. They design an oscillator that's fairly indifferent to frequency. It's just an LC network. But they take special pains for output stability and level. And I'm surprised that I can take a 436 that's 20 some years old and put it on the power meter, and it's still within spec. So the uncertainty calculator comes out with 11.8% total uncertainty for reading. It's not of 11% full scale. It's of reading. So that makes it a little bit easier. I think you can get it down to 6% if you work on some of those levels of uncertainty. And I think it's important because if you're dealing with especially high-powered amplifiers, one of the things you have to fight is efficiency. Spectrum amplifiers are 40% or 35% efficient at 2.5 gigahertz. If you're off and you think you're getting more output than you are, the rest of what you don't know you're doing is heat, and you can really heat up an amplifier like that, and those transistors do not like lots of heat. So it helps you constrain the amount of inaccuracy in terms of efficiency for the amplifier. Okay, next slide. So modern meters like the HP or Keysight 4418 and the Anritsu 3437, they try to do a lot of work on taking out some of the biggest errors like having an EEPROM that stores the correction factors. So when you plug it into the meter, it automatically sets all that up, and you just tell it you're working at 10 gigahertz, and you're not making a mistake, because I'm sure that they found that on a practical level, technician level, that people were making a mistake with the compensation settings and getting wrong readings. So that helps. There are compensations for temperature, and there's some back-end DSP that helps on averaging and getting a more consistent result. The N432A that 478 heads is in a class by itself, and that's all I'm going to say. If you like it, if it's a great idea for you, and you have a spare $8,800, instead of getting that new Tesla car, you can go check with your HP dealer and get one. But then let us know. Yeah, of course, in the junkyard. Then let us know, and we'll all send you our power heads for measurements if you buy an N432A, and you'll be really popular. So, in thinking about this, a meter like the 436 may do a pretty good job if you have a calibrated sensor, especially if you use the external digital voltmeter technique. So you may be farther ahead having a fairly inexpensive meter, but spending the real money on a very good power head and taking care of it, which means don't drop it and don't put too much power on it. If it says this power sensor will take 300 milliwatts, don't you dare, because heating up that little tiny substrate in the middle of the head is gonna warp it. It won't necessarily kill it, but it'll change the accuracy significantly if you push the power level. Okay, next. Conclusion. SWR of the load and sensor are key factors. Sensor linearity is largely unknown unless you specifically measure it. And as I said, a great sensor and a cheaper meter is a good compromise. And next slide. Let's see if there's the next slide. These are the resources. The HP app note 641C is really good. If you can find a PRD calorimeter manual, it really gives you a nice background of calorimetry. And the 2400 series Anritsu power manual is good. These two linkable PDFs didn't show up. So if down at the bottom, the talk is available on Ryan Schmidt's W6SZ's nighthawk.com website, and you look up K6KEY talks. And this talk, as well as one of the PDFs, is on that site. So you can access that after the conference, or right now if you want to. Let's see if there's another slide. Okay, well, one more, see if it does it. There we go. Here's a sensor linearity record I put in there in case you want to check on yours. This is a standard form that shows you the allowable inaccuracy widths, and then you put your number in there and you can see how good your meter is. I thought that would, or your sensor is. I thought that would be helpful. Okay, that's it. Thank you. Okay.
Hi, my question has to do with the difference between the calibrated value that you get on 8481A at 10 gigahertz and how much it's likely to change at 24 gigahertz, as based on your experience.
No, I didn't. Oh, good. Okay, yeah. I have no experience doing that. I have a 24 gig power head, but looking at the data, it would be usable. It just wouldn't be tremendously accurate.
Hi, Doug. I don't know if you can hear me. Can Doug hear me directly? Okay. We often use attenuators to fix mismatch problems in ham radio. Unfortunately, attenuators values are only correct at 50 ohms, so I wonder if inserting attenuators can help with the mismatch problem in power measurement.
Oh, okay. I don't think so, because you don't know the attenuator value unless you want to measure it very well at frequency. If you can do that and factor in the mismatch of the attenuator and the value of attenuation at that frequency, that would help. But now you've got at least a 3-axis problem of mismatch, and in terms of the real accurate connections, tenths of an ohm make a fairly big difference. So if you're off by 0.3 of an ohm, I wouldn't even hook it up, and that would be the major factor, I think. And then what it does at frequency at 10 gigahertz, you're really kind of in unknown territory for highly accurate measurements.
Yeah, I got a couple of questions, actually, if we can handle more than one. One at a time. Okay.
One at a time.
You didn't.
Thank you.
I've got, what is it? The 487, which is a little thermistor power meter that I've used a lot. There's a efficiency calibration chart that goes with those things. Can you say a little bit about that? In fact, I've got some other sensors that don't have that chart, and want to know how that's created. 478, excuse me, yeah. Yeah, how and if you don't have one, how do you make one?
I'm going to assume that the efficiency is the compensation for frequency. Is that right?
I guess that's what it is. And there's a little knob on the front of the instrument that you can.
Oh, I think the only way you can do that is to get a known power source, a signal generator that you know is accurate from another power meter, set the frequency, say 10 gigahertz, and run your efficiency knob until you get the correct power reading, and do it backwards that way.
Okay. The next question I have is that the 432 had a little calibration box that you could connect to the bridge in the instrument. Have you had? I don't remember what the model number is, but have you had any experience with that? And can you say what that gives you? Go ahead. Yeah, that's right. That's what it is. Yeah. That's the one that calibrates the actual meter. Okay. Yeah, I have one of those, and it's for sale again. It was very accurate when I got it. It took almost no calibration, and the box, the 436 or whatever as I measured, really wasn't off enough to fiddle with it. It gives you the security of knowing your meter's right, and with some of the meters we get, you'll want to check it. It's a good box and very stable. And the third question I had is about the 434. I've got one of those, and I've hung on to it primarily because I figured I could calibrate it with DC, and I had given some thought about building a new display for it, and I want to know whether might be worth doing. That's the old calorimeter that you put the oil in.
That's the oil-based calorimeter.
Yeah.
Okay. Your biggest problem with oil-based calorimeter is keeping it going and finding oil. Do you have it functioning at this point?
Yeah, I figured out what the oil was and bought some off of eBay.
What? My gosh, what oil was it?
It's
It's a Dow
actually
Corning, like 100 weight oil.
no, it's 1 cent a stroke or whatever. I can't remember what the thing is, and it's actually used in foodstuffs. It's a mineral oil.
Okay, that would be helpful. The yes, you could bridge a digital voltmeter across it and increase the accuracy of the meter reading, but I think I'm going to go out on a limb and say I think the actual DC meter on the front reads at the limit of the accuracy of the calorimeter, because it's 1%, 2% reading. But the nice thing with that meter, and it's one of my favorites, is it goes from a very low power to 10 watts over an extremely wide frequency range. And if you're gonna align duplexers for a repeater, it's a piece of cake with this thing. But I long ago got rid of mine when it leaked oil.
I have actually 2 of those oil calorimeters, and it's 1 centipoise silicon oil, and I've got 3 different manuals from HP, and only one of the manuals listed what the oil actually was. I ordered it, one of the instrument supply houses. They said it was only made once a year, and I had to wait 6 months to get it for $90 for a quart.
Yeah,
This is getting hard to translate. You got it.
yeah, I did. I had heard that they made only 150-gallon drum of it in 1965, and they ran out. And I know guys that worked in labs in the Hughes aircraft that when they knew the things were being surplused out, they put the oil in mason jars and kept it in their garage. And I got a quart of it, I think, from a guy in Palos Verdes. But it's almost like a cult. If you know how good that meter is, you'll do anything to keep it going. And I completely agree. It's really a very versatile meter that hasn't been replaced. Bird makes a meter, but doesn't have the frequency range, and it's $14,000. Okay. This has been fun. Okay. Mhm. Well, if you're going to calibrate like a 436 or 7 or 8 meter, there are only 2 adjustments, and one is the frequency of the calibrate signal, which is plus or minus 10 megahertz, something like that, and then the other is the level calibration. And of the meters I have not seen a very big difference between calibrator outputs, and that includes going back to the thermopile, using that as a transfer standard. That's puzzling. Yeah.
Much, Doug. This has been a great presentation, and the technology actually worked. So
Yes.
we'll move over and we'll now do our we're going
Sneak another auction.
to sneak another auction in.
Before he gets it away, this is kind of related to his car.
We have a thermistor mount. What's the number?
It's a J486 Alpha, 100 ohm type.
J46 Alpha waveguide.
It's a waveguide. What size did you say it was?
That's J-band, and that's good from 5.85 to 8.2, I believe.
So it's close enough for 5760.
5760.
It'll probably work fine at 10 gigahertz.
Yeah, you just need some adapters.
There you go. Yeah, just
need
need.
to adapt it. Yeah.
Doug, since you talked about these, I'll give you first crack at it. You interested?
No thanks.
Okay. Well, that's all right.
I just happen to have some of that.
Yeah, I'm going to auction it off on this end then. So.
Okay. Well,
Okay.
let me say goodbye and thank you very much. And it certainly has been a pleasure.
Yeah. Thanks a lot, Doug.
Okay.